Thank you for coming to our presentation today. We are going to talk to you about our machine learning project, which is our hypothyroid dataset. Alright, now we are presenting you our group members, which is me, Nurul Izzat Zainal binti Rahaizat, Siti Audi, Siti Mariam, and also Putri Nurul Shazwani. Let's start with the introduction. What is hypothyroid? Hypothyroid is a type of chronic disease that could also affect other diseases in the body. Thyroid is a butterfly-shaped gland which is located at the bottom of the throat that is responsible for producing two types of active thyroid hormones, levothyroxine, abbreviated as T4, and trioiodothyronine, abbreviated as T3, that affect some functions of the body. These functions include stabilizing body temperature, blood pressure, and regulating the heart rate. People suffering from thyroid gland tend to fall sick due to the under or overproduction of hormones from this gland. Okay, let's start with our problem statement. Our problem statement is to implement BPNN accordingly to classify the hypothyroid. And we decided to go with the BPNN machine learning algorithm. We have a few type of test options that utilizes percentage speed, learning rate, and epoch. We use a lot of variables differences in each.
We will continue with the data processor for hypothyroid dataset. The hypothyroid dataset that we chose is from Kaggle. It has 26 attributes and 3,164 instances. It consists of numeric and nominal attributes. It also has missing values that need to be handled. Next, we use vector to identify the outlier and extreme values from the dataset. Then, we decide to remove it as it is not needed in the dataset using remove with values filter in vector. Here, we can see the result after removing both the outlier and extreme. From the chart, we can see that the dataset is biased towards negative values, where the negative value is 2,791, while hypothyroid only has a total of 42. So we decide to resample the dataset using synthetic minority oversampling technique, which is also known as smooth method, to keep the balance between hypothyroid and negative values. Then we use Python to continue dealing with the dataset. This is the code that we use to rename the first column in the dataset. It is because the first column name in hypothyroid dataset is unknown, so we name it as class of the dataset. Next, this code is to check the attribute of the class instances. We can also get the total count for hypothyroid and negative values like in VK. Next. Based on research paper titled Thyroid Diagnosis Based Technique on Raster with Modified Similarity Relation, we decide to remove some of the attributes as it is unnecessary for our dataset. The 8 attributes that is shown in the slide is age, sex, choline hypothyroid, lithium, T3 measured, T4U, TBD measured, and TBD. We have also extracted some rules that have been mentioned in the research paper to see how it affects our accuracy in order to build a better model. Next, since the dataset for some attribute is numeric, we need to change it to nominal type before proceeding into testing the result. Here, all the attribute with categorical data type is changed into nominal type, which is in binary values.
Okay, the next one, since the dataset has some missing values, they have to be replaced with other values. And this is the process of replacing the missing values in the dataset into none values before replacing them into mean values. None is stand for not a number, and it still can be run for BPNN because none is considered as special floating point value. Okay, next one, we convert the attribute data into numeric values because BPNN can only process numeric values. The picture shows the data type of the attributes after they are converted into numeric values. There are some of the attributes have integer data type and also some attribute has floating point data types. Okay, the next one, we replace the non-values into mean values. We replace the attributes TSH, T3, TT4, and FTI into mean values of the attributes. Okay, after that, we normalize the dataset using the min-max scalar, and this process is to normalize and standardize the data between the range from 0 to 1. Okay, and this is the description of the data. It shows the count of every attribute, mean, standard deviation, minimum value, quartiles, and also the maximum value of every attributes in the data set. Okay, after the pre-processing process, we will split the data into training data and testing data. And this is an example of the splitting process. We split the data into 70% of training data and 30% of testing data. And the testing data size can be changed by changing the number at test size.
Okay, next we proceed to the neural network architecture design. Okay, this is our BPNN architecture based on our dataset Hypothyroid, which consists of 17 input nodes, 4 hidden layers, and 1 output. And then the pre-processing data technique that we applied, it was referred on the research paper that was mentioned previously by Putri Nur Shazwani. It's called Thyroid Diagnosis-Based Technique on Rough Set with Modified Similarity Relations. And we have managed to extract and remove a few attributes that's been mentioned in the paper, and we apply into our BPNN architecture algorithm. Okay, for our BPN algorithm, for our parameters, of course, we need to have learning rate, epoch, n is equivalent to the number of the element in the level matrix that correspond to the number of the element on the output matrix. And we also need to have a input, hidden, and output. The function that we use in our algorithm is, of course, sigmoid function, mean squared error function, and lastly, accuracy function. And we also need to initialize the weight. There are 2 weights that we initialize in our algorithm, which is weight 1 and weight 2. Weight 1 is used, is applied between input and hidden layer, and for weight 2 is applied between the hidden and output layer, and the both weight are set to scale at 0.5. Okay, this is our BPNN algorithm, the process. It shows you firstly inside epoch. For every epoch, it will apply feed-forward function, feed-forward algorithm, which is first we set the hidden layers. We apply the CMOD functions, multiply by the input matrix with weight matrix 1. And for the output layer, we also apply CMOD function and then multiply by the hidden layer and the weight matrix 2. And next, we also calculate the mean square error. Mean square error is the average square difference between the predicted values and the actual values. It will monitor the training process. So the two variables that will monitor the training process, of course, the MSE and accuracy. And then this is our MSE. We set the MSE equals to mean square error to output layer, and the Y train is equivalent to the test set. And accuracy, we take the output layer and the test set also. And then the mean square error and accuracy will be monitored and append in every epoch. Next, of course, in BPNN, there will be backpropagation. Okay, we set output data and hidden data. For output data, we'll take the output layer subtracted by the output matrix and multiply by the roots of the sigmoid function of the output layer. And for the hidden delta, we'll take the output data multiplied by the transpose of the weight matrix 2 due to the difference dimension and multiplied by the roots of the sigmoid function of the hidden layer. And lastly, of course, every time we did the backpropagation favor, we have to update the weight. Okay, we can do that by subtracting the learning rate and multiply it by the hidden layer transpose and the output data for weight 2. And for weight 1, we will subtract the learning rate and multiply it by the training set and the hidden delta. Okay, after we apply the BPNN algorithm, we will train the model. Okay, as you can see, this from this picture is an example of a sample output for our training model with 600 inputs with a learning rate of 0.5. As you can see, starting from 0, the accuracy at 0 was 0.476527, and by the time it was at 600 inputs, the accuracy keeps on increasing. So from there, we can see how the data, the input makes the data, the accuracy increases. Next, we also apply in our Python, our project is to display the accuracy and the mean square error. We display in a graph based on the model training previously. As you can see, as the epoch, the number of epoch increases, the mean square error decreases. And for accuracy, the accuracy increases as the number of epoch also increases.
And next is our result. Okay, 50% training, 20% testing data, and also 90% training data and 10% testing data. And we also tested our network with a few different epoch numbers and different learning rates. Based on the 80% training data and 20% of testing data, this is our result where we get 88.01% of accuracy, which is the highest accuracy out of all of the test options. Okay, this is the formula and functions that we use to produce the conversion metric for our BPNN. We use the built-in function from sklearn in order to produce our conversion metrics. Okay, this is the output. This is our conversion metric that we produced from our neural network, and we got 474 true positive, 53 false negative, 83 false positive, and also 524 true positive, and the accuracy of 0.88.
Alright, let's move on to our findings, which is the final part of this project. For our finding, by the end of our experiment, the highest accuracy that we have managed to get was 88.01%, with the 80% training and 20% test set. The epoch that we have settled with is 900 with learning rate of 1.00. Alright, let's look at our result analysis. This is our result analysis for 70% training set and 30% training set, test set. As you can see, the highest accuracy that we have managed to get is 87.71%, which is both for epoch 900 and 1000 for learning rate 0.9 and 1.00. As you can see, this is our graph for our for 70%, 30% split, percentage split for epoch 0 for epoch for learning rate 0.5, 0.6, 0.7, 0.8, 0.9, and 1 with various epoch. This is our result analysis for 80% training set and 20% test set. As you can see, the highest accuracy is 88.01 for learning rate 0.9, epoch 1000, and also epoch 900 with learning rate 1.0. This is our accuracy for each learning rate 0.5, 0.6, 0.7, 0.8, 0.9, and 1 for percentage split 80, 20 with various epoch. Okay, let's move on to our last result analysis, which is training set 90% and test set 10%. As you can see, the highest accuracy is 86.60% with epoch 1000 with learning rate 0.9 and also EPUB 900 with learning rate 1.00. This is our graph for percentage fit 90-10 for various learning rate 0.5, 0.6, 0.7, 0.8, 0.9 and 1 for various EPUB. Alright, let's move on to our references. We have multiple references that we have included. Okay, the main reference would be our thyroid diagnosis based technique on rough sets with modified similarity relation by Il Said Radwan by year 2013. Next, we have data mining classification on hypothyroid detection, association women outnumber women by Suwarna Goten 2020. And lastly, a study on label TSH, T3, T4U, T4, FTI in hyperthyroidism and hypothyroidism using machine learning techniques by Suwarna Gotan 2020. And also we have a few references for our coding for a neural network from scratch in Python by Sebastian Mati. That is all from us today. Thank you for watching.